So Murilo was talking, he made a comment about making a talk just after lunch, and I'll tell you a secret. When I registered my talk, they asked about the available times, and I said, no, I'm not going to be able to give a talk just after lunch, just because I know people is going to be sleepy. So that's why you had to do that. I'm going to talk about CPU vulnerabilities and KVM security. It's basically about the new families of CPU vulnerabilities that started with Meltdown and Spectre in 2018, and how they affected KVM. I'm not going to focus on the details of the vulnerabilities, but on how we needed to change lots of components of the KVM stack, of the virtualization stack, to deal with that. So I'll start showing some of the configuration abstractions used in KVM. I'll show how things fall apart, how things break because of that, and what we are working on today. So I'm going to ask, how many of you use virtualization or run virtual machines on your desktop or on a server? How many of you run QEMU directly to do that? How many of you use libvirt or are aware of using libvirt? How many of you will use Virt Manager? How many of you use OpenSec? Other stuff you use, what do you use when you are running virtual machines? Other tools I didn't mention. Nope, okay. Good, so because I thought many people would run QEMU directly and not use libvirt, but it seems to be the opposite. And that's good news for what I'm going to talk about. So these are the layers we have on the virtualization stack I'm going to talk about. You can change this component, so some people might not use QEMU, some people might not use libvirt. Some people might use libvirt directly and not use a management application. But this is basically the layers I'm going to mention. So you have the hardware, the KVM code that interacts with the hardware that Murilo talked about. Then we have QEMU, that's a user space component. We have libvirt, that's a library that's a layer above that. It helps you use QEMU, helps you manage things, do things that QEMU won't do for you. And on top of that, you have the application that will use libvirt. So let's talk about the abstractions we have today. The focus of the talk is going to be x86, because most of the recent vulnerabilities were on Intel and AMD platforms, but some of the details might apply to others. So the starting point of everything we're going to talk about is the Cpi T instruction on the x86. So Cpi T is a very low-level interface where you can ask the CPU for information about what it can do. And basically, you give the instruction one number or two numbers, and you get lots of other numbers back. And this is the data you get back. You can run this command, these two, x86 info, and you can see the raw Cpi T data. But it is very low level. You are not expected to understand all these numbers. And normally you look at something more friendly. That is, for example, the CPU info file on Linux. On the CPU info file, you can see a human-friendly description of what the CPU can do. And most of the data there comes from the Cpi T instruction. I have highlighted the flags line there because the most interesting data is there. Have lots of flags. I think I'll get here so I can see. And it's basically how the CPU indicates that something changed. So you install a new CPU, you buy a new computer, you're going to get a different set of flags indicating what the CPU can do. And now we are getting to KVM. So basically, this is something related to what Murilo was talking about. KVM controls all the Cpi T data seen by the guest operating system. the guest operating system is not going to see everything that's on the host. It's completely controlled by KVM, and it's completely controlled by QEMU. This is the IOCTL call that QEMU does to do that. So the details from the host are always hidden. But even if that's not, even if the guest can't have access to everything, you probably want the guest to see that. So if you install a new version of the kernel that supports a new feature, you install a new CPU, you add a new server to your cluster, you probably want all your guests on a VM to have access to the new features. So that's why the simplest mode you can use with KVM is host pass-through. Host pass-through means you are going to get all the features that are supported by the hardware and the software, and you're going to expose to the guest. And it's important to note that you're not going to expose all the hardware features to the guests. Even if you use that, you're going to expose only the ones that are supported by KVM as well. So that's an important detail because the hardware is always hidden from the guest. But we have something that makes it more difficult. That's called live migration. So if you are running KVM on your desktop, you have a single virtual machine, host pass-through is perfect. And if everybody was using host pass-through, this talk would end right now, because now you say, okay, just update KVM, update your microcode, update your guest operating system, restart everything, and you're okay. But then we have live migration. Live migration makes everything more complex on the virtualization side, because live migration lets you get a VM that's running on one machine, move to another machine while it's still running. Even if that machine has a completely different CPU, that machine might have different sets of vulnerabilities, and different versions of the software stack, so you can have a different kernel, a different libvirt version, a different QEMU version, and the VM will still be running during that. But the operating systems don't expect the Cpi data to change. So a virtual machine is pretending it's a real machine, and real machines don't change the CPU when they are running. So you need to do something that make not break. And that's why this can't work with host pass-through, because hosts are different. I mean, if you keep everything under control, if your host is exactly has the same CPU, same kernel version, same QEMU version, maybe it will work. But let's just assume it's not going to happen, because it's very difficult to make sure that's the case. So we need something that we call predefined CPU models. So that's when we are starting adding new abstractions to deal with that. And this is how it looks like on QEMU. Predefined CPU models are names to a set of CPU ID data you want to expose to the guest. So the guest is going to see a fake CPU that looks like what was defined in a table inside QEMU. So this is just a small part of the list. If you ask for CPU help using the -CPU option, and it's huge. You have a huge list of CPU models. And if you are using the same CPU model with the same QEMU configurations, you are going to get the same CPU ID data. Even if you upgrade QEMU, that's the trick. Even if you upgrade your kernel, you upgrade QEMU, if you are using the same CPU model, the CPU ID data will be the same. That's the biggest assumption we have in this whole system. Continuing with the CPU models, this is an example of a QMP command. A QMP is a protocol used by software to talk to QEMU. It basically allows you to do everything you can do on the command line, plus something else that software can use. So in this example, I'm showing two CPU models from the list, when we are asking QEMU for the list of CPU models. And then you can see the list of unavailable features on that CPU model that says, okay, on this machine, I run that on my laptop. On this machine, I can use the Skylake client CPU model because every feature is available, but I can't use this one because some features are not available here. So this CPU model can't be used. And then libvirt can use that, expose that to the libvirt API. That looks like this. I mean, this is how you choose the CPU model on libvirt. Normally, you're not going to deal with libvirt XML directly. You're going to use a user interface, but this is how it works on the inside. And then you have something more complex. I won't go into details. That's, for example, one function on the libvirt API that you get a list of CPU modules and compute what's the, for example, you get information from multiple machines, and you can compute what CPU model you can use that will run on all those machines. It's useful if you have a cluster. So you have multiple different machines, you can ask, okay, what CPU model I can choose here? And this, I don't need to explain it to details, but libvirt gives you this API. And finally, you have the user interface, where all this complexity is hidden. Just list, and you can say, okay, please use this CPU model, or you can say, please just copy this whole CPU, and everything is going to work. In addition to that, you have a special mode that does not exist in QEMU, but it exists in libvirt, to make this a little bit easier. That's called host model. Host model is basically getting the best of both worlds. You are going to get a CPU model that has everything from the machine you're running, but it can still live migrate it, because instead of just exposing everything to the guest, it's going to copy this information to the XML configuration on libvirt, and it's going to stay there. And after it's already there, you can migrate it, because this XML data is going to be on the other side. The CPU will be on the other side, and everything will work. You can live migrate. So this is where things work. These are the abstractions we have. Do you have any specific questions about how things work? Yes?
So in the case of host model, there may be a situation in which some of the features in your machine are not available in the processor of the other machine. So in this case, will QEMU emulate these features, or no? Because how will you migrate if all the features are not available in the destination?
Normally, nothing will be emulated. There are very few exceptions on KVM case, but normally, if my laptop has a few features, my server doesn't have a few features, your server have extra features, and I use host model, I'm not going to be able to migrate my VM to your machine. So then you can use the other more advanced libvirt APIs to compute what's a good CPU model that can run everywhere.
Is it possible to forward to a different set of CPUs or different hypervisor some kind of request? Supposing that we have, let's say, that we have a bunch of host machines, right, which share the same CPU model, and I can move from a box to another, but let's say, okay, we don't have it here, but we have someone outside that perhaps could do that.
Yeah, I mean, so I'll try to repeat your question for the video. So you asked if if I have lots of machines with a single CPU model, if I can move the VM outside, but okay, so I run it here, but use something remote. Oh, it's tricky. I mean, in theory, you can do everything with virtualization. So for devices, this might happen. So you can forward a video device, you can forward a USB device, but a CPU, if you're using another CPU, you're actually basically running the code there. So we don't have that. We have something that you can move the VM there, but you don't have anything that you can run half of the CPUs here and half of the CPUs everywhere else. It could be possible, but I never saw anybody do that. Yeah, it's difficult. And the most difficult part would be, I mean, CPUs share memory. So running something separate, it's going to be difficult to make it work. So let's see when everything breaks. This is something I like to quote a lot when I'm going to talk about something that breaks. It's the Law of Leaky Abstractions. It was coined by Joe Spolsky in 2002. Oh, that's a long time ago. I was so young. And it says, all non-trivial abstractions. An abstraction is something that will simplify something for you, that will hide the details for you. To some degree are leaky. That means you can't hide everything. Sometimes you try to hide the complexities, but then the real world comes and says, okay, you're not going to be able to hide these details. And this is what happens here. So what are the details we are trying to hide here? We are using CPU models to hide what's inside a real CPU and saying, please just use a CPU model and it's going to work. The first time this broke was in 2014. This is not even a CPU vulnerability, it's a CPU bug that was found on the TSX feature. I don't remember what it means. It's something with transaction something S for something, extensions. And they found some issues, and it was basically completely broken, and they released a microcode update that disabled the feature completely. And now we have a problem because we have, it was on the Haswell and Broadwell CPU models, and we have Haswell CPU models, Broadwell CPU models, in QEMU saying that TSX is available. And now you upgrade your microcode, and your virtual machine can't run anymore because you don't have those features. So yeah, that's basically what I said, and this is the solution we had to adopt. Adding a new CPU model saying, okay, we have the original Broadwell CPU, and then the new Broadwell no TSX CPU model. It seems simple, not so bad. You have only 2 new CPU models. It works. Okay. Yeah. You cannot live migrate. So you have Broadwell with an old microcode, Broadwell with new microcode. You start a VM here, you can migrate there. Or you create a VM here, shut it down, copy the configuration, it doesn't run anymore. Or you install a software update, shut down your machine, reboot your machine, the new microcode will be active, your VM won't boot anymore. So yeah, it was already annoying. Then we have the vulnerabilities that started it all. The first speculative execution related vulnerabilities that were Meltdown and Spectre. And the nightmare began. Meltdown was bad, but not for KVM. Meltdown, the mitigation for Meltdown was only on the software side. We changed how Linux deal with the page tables changes. It has some overhead, but it works. You just need to make sure you update your host OS and your guest OS because both are independent, and you need the host OS to protect the processes on the host, and you also need the guest OS to do the same, but no KVM specific changes. But then we have Spectre. The mitigation for Spectre, and it's not a fix, it's a mitigation. The mitigation means you're trying to avoid the issue or didn't fix the issue. Involves a microcode update and software updates to use this microcode update. The microcode update adds a new feature to CPU ID. It's called spec control on Intel and IBPB on AMD. And now we have something similar to TSX, but now we have new features. And this is what we have to do. This is where we start to feel a bit ridiculous. I don't know if I can move this. Yeah. So you have the AMD EPIC CPU model is easy. You have EPIC and EPIC IBPB. Broadel, we have Broadel and Broadel no TSX, and now you have Broadel IBRS, Broadel no TSX IBRS, and the same for all of them. So it's starting to look like this is not the best idea, the best we can do. And May 2018, another vulnerability, SSB, it's speculative store bypass. And the details are different, but the mitigation is similar. We have a new microcode update. We need software change to use new features. The new features are reported on the CPU. On this case, we also have a virtualization-specific flag. I don't remember the details, but I think you can emulate the new functionality on the host side, so you can say, okay, I'm a virtual host, and I can emulate the same feature that is available on the microcode updates. And this is where we decided, okay, we are not going to add new CPU modules anymore. We are going to expect virtualization software to add the new flags on demand. I mean, you're going to just use the Skylake client IBRS CPU model plus the SSBD flag. And you need to do that to ensure that this new feature is going to be available to the guests, so the guests can use it. And this is on the QEMU side. On the delivery side, it's good, because you just need to use host pass-through. Like I said, if you use host pass-through, you don't need to even watch this talk. And if you're using host model, it's also going to work, because host model is going to be translated to this CPU model plus this and this and this and this feature. So the new features are going to be enabled automatically. It's kind of good. August 2018, L1TF. This one, I was not sure if I was going to include, because it doesn't affect KVM directly, but it affects people using KVM, so I want to mention that, because it's a software-based mitigation. You don't have new CPU ID flags, but if you are not using virtualization, everything is going to work, because the mitigation is not expensive. It won't impact performance very much. But if you're using virtualization, the guests can attack the host very easily. If you are using hyperthreading, and then you have a very difficult decision, because if you disable hyperthreading on your CPU, maybe you're going to have half of the performance, and this can't be enabled by default. So the solution for L1TF is a bit more complex. You just need to type this URL on your browser, read a 10-page document. I don't know how long it is, but you need to choose between 5 different alternatives. None of them are perfect, and see what you can do. Luckily, I mean, the good news is that I didn't have to do nothing for this bug, because it didn't affect KVM, it didn't affect QEMU, but you still need to be aware of it. And now this is becoming repetitive. MDS, microcode update, software update, new feature. You need to add new feature to the CPU configuration, but you can use host model. So this is basically how things are working today. But that's not all. There's something I have hidden from you. So since Spectre and Meltdown were introduced, we have something new on the Intel CPUs. That's a new MSR called Arch Capabilities. AMSR is a model-specific register. It's basically it's a CPU register. that indicates that the CPU is not vulnerable to something. So you have bits on that MSR saying, oh, I'm not vulnerable to Spectre variation 1, I'm not vulnerable to MDS. And we need to expose that to guests, but this is not CPU ID data. And then we needed to add a new functionality to KVM, a new API, where in addition to that IOCTL I showed, set CPU ID, you need to also query what are the MSR values for this current host. You need to set it, and you need to include this data in the CPU model information. The good news is that this is not required for mitigation, so I think that's why they did this separation. The CPU ID data says, this CPU has this instruction, you can use it, and then you can use it to mitigate the bug. The MSR says, this CPU is not vulnerable. So the effect here is not that you're going to stay vulnerable. The effect is that the guest will think you're vulnerable because you are not. So you have a CPU that's fixed. It's not vulnerable anymore to that bug. You can see that, but inside the guest will think it's not vulnerable. It looks bad, but it's actually a good idea because remember live migration? You want to be able to migrate to another host. So what if you tell the guest, you say, okay, you're not vulnerable, don't worry, and then you live migrate your VM to a CPU that's vulnerable. So you need to be very, very careful. So that's why we don't enable it by default. But these make things more complex because just like the rest, you need to enable Arch capability bits manually on the QEMU command line, or you need to use host model. Okay. So it's basically a summary of what's broken. And now I try to explain what we are trying to do to make this a little bit better. So what's the big issue here? Is that host model works, host pass-through works, but it's not the best solution for everyone. Sometimes you want to make sure, okay, I have a cluster of machines and I know I have some older CPU there, and I can't just use the whole CPU by default. I need to configure it manually and say, okay, I know I have this Skylake, and because I need to migrate to that Skylake host, even if this one is much newer CPU. And when you do that, you get the same problems you have for the QEMU manual configuration. That's this. If you're not using host model, you need to do something equivalent to this on the libvirt configuration, and it's really easy to get it wrong. It's really easy to forget something. So what we are trying to do is something called version CPU models. At first look, it doesn't look much better than what we had. So now we have 4 different versions of Broadwell. That's basically what we had. And we have aliases that says, okay, if you're using this one, actually it's the first version, second version, third version. What's the difference? The difference is going to be on the APIs we expose to the upper layers. We did this on QEMU side. The libvirt work is in progress. Because we want people, when you're using Virt Manager, we want you to just see a small list of CPU models, but after you choose that, you're going to get the best version possible automatically. And this is why we are introducing this new abstraction saying, okay, you have new different versions of CPU model, and then you can just say, okay, give the last version, or tell me what I can run here, what I can run there. Questions? I didn't have much detail about this, so if you have questions about how that will work, I can try to explain.
Are you working to be able to always migrate to the next version? I mean, is there any logic between the versions or not?
I'd like to, but guess operating systems don't expect the CPU data to change. This fact didn't change, so There's no way. You can always migrate to a new one, but the guest will still think the CPU is old.
Sure.
That's the main problem we have. So, and this is maybe the root cause of all of this. There are two root causes of all the problems we had. The first one is that the operating system doesn't expect the CPU to change. It's hard to change that. The second fact is that we assumed, all the layers we had there, assumed that same CPU model means same CPU data. And these we are going to change. So with the versions, with the aliases, now we have something that has a name, but can change to make it easier for users. So trying to summarize recommendations, just as reminders. Remember to update the guest and host software when you have new security updates. Use host pass-through if you can. If this talk was 5 years ago, I think I would say maybe you can use host pass-through. It's not reliable, but today it's much more reliable. Best option you can have. If you can't, try to use host model. If you can't, then you probably need to be very careful today and wait until we have a better API, until libvirt is adapted, until the management applications are adapted to make smart decisions. Pay attention to L1TF because mitigation is not enabled by default. You need to pay attention to hyperthreading. You can try to isolate the VMs on separate CPUs if you want to disable hyperthreading. You can always check seize device system CPU vulnerabilities to check what's happening on your host to be aware of that. Just remember that when you do that inside the guest, you might get false alarms, and that's on purpose. Because if we are unsure that VM is going to be migrated to an unsafe CPU, the vulnerabilities will be reported as present, even if the host is not vulnerable. But it's a good idea to always check that. And that's all. Now we can have more questions.
Actually, I have one.
Yep.
So you mentioned that these flags, they are added like a whitelist flags. So if the host CPU is not vulnerable, if the host CPU is not vulnerable, but then you don't tell it to the guest, then it feels like the guest CPU thinks that it is vulnerable. So can you change this after some time? So for some VMs, you want to say, yeah, I am vulnerable. But for others on the same host, you say, no, I'm not vulnerable.
You can change that on your configuration. I'm not sure we can change the default. So changing defaults on this stack is very difficult for multiple reasons. One of them is compatibility, because at the QEMU level and at the libvirt level, the expectation is if your configuration is the same, the virtual machine will look exactly the same. So if today we don't enable this by default, we try to not change that and start and change the semantics of the configuration file. So we delegate that to the upper layers. But with the version CPU models, it's going to be easier to change the default. So with the version CPU models, we can, in the future, add a new version of all CPU models that say, I'm not vulnerable. And this new version won't run on vulnerable CPUs. And we can do that. That's one of the advantages of the new system. So we are going to be able to add a new version. And this will keep working because old software, we will use the old version. New software will ask for the latest version. It will work. Or maybe new software will ask for the latest version, but it will see that the latest version is not available everywhere, then you're using a slightly older one. So yes, we can change it. With the version CPU models, with the aliases, we'll be able to change the defaults finally and say, okay, we're not vulnerable because it's a 10-year-old, maybe 20 years now. You're going to say, okay, nobody will have a CPU that's vulnerable, let's just change the default. But we need to give time to the upper layers to adapt before changing the defaults. That's the difficult part. So I can't enable this on the QEMU side. I need liver to adapt and say, okay, please give me the latest version. And then we need the users of liver to adapt and say to liver, please enable this new behavior. And then we can do that.
No more questions. Thank you all.
Thank you.